Assalamualaikum and hello to everyone. In this video lesson, we will continue with chapter 5 of our syllabus. In this video lesson, we will cover the fourth subtopic as highlighted on the left. The objective for the subtopic is on the right of the screen. Now, the second method which we can use to improve the performance of a Brayton cycle is by reducing the work input at the compressor. This is achieved by using the intercooling process, which is done by adding an intercooler to allow for multi-stage compression within the cycle. The intercooling process is located at an intermediate pressure, also known as the intercooling pressure. For minimum work input during the multi-stage compression process, the temperature at the exit of the intercooler, T3, is the same or equal to the temperature at state 1. Now, even though there is a multi-stage compression process, the total work input by the compressors is smaller than a single-stage compression process. As mentioned previously, the effect of the intercooling process is that the total work input by the compressors will be smaller. Under ideal conditions, the following equations can be used to calculate for amount of work input at each of the compressor. Under actual conditions, the following equations can be used to calculate for amount of work input at each of the compressor. Remember that for actual conditions, please apply the isentropic efficiency equation at the required compressor. Now, let us look at an example for Brayton cycle with intercooling process. You can pause the video to read and understand the question properly. Now, from the question, since there is no mention for isentropic efficiency, the cycle is assumed to be working under ideal conditions. For step 1, please refer to the notes and try to draw and label the required cycle. For step 2, write what is required or equations. Now, based on the question and also the schematic diagram drawn in step 1, the temperature of the gas leaving the turbine is located at state 6. To solve for mass flow rate, since the amount of work produced is given, we can use the following equation to solve for the mass flow rate, but remember to solve for work net first separately. To solve for back work ratio, it is simply the amount of work input, which we have calculated previously, divided with the amount of work output. And finally, for thermal efficiency, the following equation can be used to calculate the thermal efficiency. But remember to calculate the amount of heat added individually first at the heat exchanger. Now, for step 3, determine the required properties at each of the state. At state 1, from the question, the values for pressure and also the temperature already given in units Kelvin, so we have to simply write it down back. At state 2, since the process 1 to 2 is an isentropic compression at the first compressor, we will use the entropy relationship equation for gases to find the ideal temperature here at state 2. At state 3, which is the state after the intercooling process, the temperature in units Kelvin is already given in the question. At state 4, since process 3 to 4 is the second isentropic compression process at the second compressor, we will use the entropy relationship equation for gases to find for the ideal temperature here at state 4. At state 5, this is where the maximum temperature for the cycle is located, because state 5 is the location after the heat addition process. Finally, at state 6, since the process 5 to 6 is an isentropic expansion inside the turbine, we will use the entropy relationship equation for gases to find for the ideal temperature here at state 6. Now, this is also the answer for the first item from the question. For step 4, substitute and solve for the required items. For mass flow rate, calculate individually the work output and work input and then solve for work net per unit mass. Then substitute the value to solve for mass flow rate based on the equation previously. For back work ratio, substitute the required values and solve for the item. Finally, for thermal efficiency, calculate the amount of heat added first inside the heat exchanger and then solve for thermal efficiency by substituting the required values. Remember to multiply the answer with 100% to get the answer in units percentage. Now we have come to the end of this video lesson. We will continue with our syllabus in the next video lesson. The next video lesson, we will look at subtopic 5.5. Thank you for your attention and have a good day.